Welcome to this lecture on subtleties and fallacies in probability. The concepts in probability can be subtle, and sometimes the answers that we get are counterintuitive. Consider, for example, a community health screening program. Let's say we have a situation where there is a liver disease which affects 1% of people in the population. We call that the base rate. 1% of the people have the disease. And we have a test for the disease, and we decide to screen all the people in the population to indicate who might have this disease. And our test has a sensitivity of 95%. So it correctly identifies the disease with 95% probability for the people who have the disease. And the specificity of the test is 98%. So the test will correctly identify as healthy a healthy person who presents for the disease, but will incorrectly identify 2% of healthy people as having the disease. These are false positive results. Now, those percentages look good, 95% and 98%. But watch and see what happens. First of all, we identify the names of the events that interest us and their probabilities. A denotes the event the person has the disease, and B denotes the event the person is classified as having the disease. From what we have already said, the probability of A is 1%, 0.01. The probability of B given A is 0.95. The probability of correct classification of someone who has the disease. And the probability of a misclassification of someone who is healthy, probability of B given not A, is 0.02. We would like to know, what is the probability of A given B? What is the probability that a person has the disease if they're classified as having the disease? That's like saying, what proportion of all the people who are sent the letters after the test saying that they may have the disease, what proportion of those people actually do have the disease? We use Bayes' theorem to calculate this probability. The probability of A given B is probability of A and B divided by the probability of B. So B are all the people who are classified as having the disease, A and B, those who are classified and who have the disease. So in the denominator, we have all the people classified as having the disease, both the people with the disease who are correctly classified, plus the people who don't have the disease who are incorrectly classified. In the numerator, we have the people who have the disease and were correctly classified as having the disease. When we work out the result, it comes to 32.42%. So less than 1/3 of all the people who were identified as perhaps having the disease actually have the disease. And the reason for this is that the data set is flooded with so many healthy people who don't have the disease that the number of incorrect results among the healthy people actually surpasses the number of correct results from the people who have the disease. So for this reason, many community screening programs have been questioned by people who point out that they cause a lot of anxiety to people who are called back for a second test, but who have no reason to be anxious because most of these people do not have the disease. Another common fallacy in statistics is the PROSECUTOR'S fallacy. And this is the fallacy of reversing the conditional. Suppose a burglary takes place, and during the prosecution, the prosecutor points out that the defendant has got glass fragments under their shirt cuffs and makes the statement that it's unlikely that an innocent person would have glass fragments under their shirt cuffs. That may be true, but the jury listening to that statement get the impression that it's unlikely for a person with glass fragments under their shirt cuffs to be innocent. But that's quite a different thing. There are lots of innocent people with glass fragments under their shirt cuffs, like people who work with glass. So saying one of these statements is not the same as saying the other. Another way of saying this same thing is if a lecturer looks around the class and says, shoplifters usually wear hoodies. That creates the humorous impression that anyone wearing a hoodie is probably a shoplifter. But again, that's not the same thing. The probability of being a shoplifter if you wear a hoodie is not the same as the probability of wearing a hoodie if you're a shoplifter. So it's true that most shoplifters wear hoodies, but it's not true that most people who wear hoodies are shoplifters. A burglary took place in Los Angeles, and the witnesses said that the perpetrator was a man with a beard and a mustache, and they gave some other details. And later on, someone was arrested and charged with this crime, and the prosecutor made the following argument as part of the case. The probability that a man has a beard is 0.1. The probability that a man has a mustache is 0.25. And then the prosecutor went on to say that the probability of a man having a beard and a mustache is 0.025. But that's incorrect, because that assumes independence. And when a man has a beard, it is very likely that he has a mustache. Those two events are not independent. Sometimes an event is referred to as being 1 in a million. Maybe a person has a certain set of characteristics. You know, they've got red hair, and they've got to wear a certain type of shoe and drive a certain type of car, and all of these combination of attributes are present in one person, and it might be said, well, this is a 1 in a million. Now, when the phrase 1 in a million is used, it can convey the idea that this event will almost never happen. However, if there's a probability of 1 in a million that something happens on an individual occasion, then it will often happen because there are many millions of people out there. So saying that something is a 1 in a million chance is not the same as saying that it's 1 in a million that it will ever happen. It's just 1 in a million that will happen in an individual case. We illustrate some probability ideas using this set of data, cross-classified by gender, male and female of some students, and the type of smartphone they have, whether iPhone or Android. The probability that a student is female is 50 over 100. We call it the marginal probability of F. It's in the margins. We're just looking at gender. We're not looking at smartphone type at all. In the same way, probability of an iPhone is 0.46. We're again just looking at the margins in relation to the type of smartphone. We're not looking at the gender details at all. If we look at female and iPhone, the probability is 0.26. That's the joint probability of F and I, as distinct from marginal probability. We can also look at the conditional probability of F given I. What's the probability that a student is female given that they have an iPhone? It's 0.5652. Or the other way around, what's the probability that a student has an iPhone given that they're female? With this data set, it's 0.52. We notice that those two are not the same. Probability of F given I is not the same as probability of I given F. Thinking they're the same is what we previously referred to as the PROSECUTO'S fallacy. We also notice that the probability of F given I is not the same as the marginal probability of F. Therefore, I and F are not independent. The probability that someone is female does depend on whether they have an iPhone with this data set. We can use De Morgan's rule to calculate the probability that someone is female or has an iPhone, probability of F or iPhone, and the simple way to do that is say, well, if they're not male with an Android, so it's 1 minus 0.03 is 0.7. The general addition rule allows us to calculate the probability that someone is female or has an iPhone. Probability of F plus the probability of I minus the probability of F and I. So I must subtract the people who are female and have an iPhone because we have added them in twice as part of the female group and as part of the iPhone group, giving us 0.7. We can calculate using the general multiplication rule the probability of F and I as probability of F times the probability of I given F. We can do the same again, probability of F and I as the probability of I times the probability of F given I. We can apply Bayes' theorem to calculate the probability of F given I, and again that gives us 0.5652. Sometimes we use the likelihood ratio, which is the odds in favour of one hypothesis. We calculate that as the probability that an event that has occurred, the probability that it would occur under one hypothesis, divided by the probability that it would have occurred under a competing hypothesis, to see which is more likely. For example, let's say an iPhone is left behind by someone. Well, was that person a female or a male? The probability of an iPhone given female is 0.52. But if it was a male, the probability of an iPhone given that the person was male was 0.4. Dividing 0.52 by 0.4 is 1.3. So we can say it's 1.3 times more likely that that iPhone left behind belongs to a female. We can combine this with other information as follows. Suppose the iPhone left behind has a pink cover. We might already know from our previous knowledge that a pink cover is 10 times more likely to belong to a female than to a male. We call that the prior odds. We now have information that has arisen statistically which tells us that the likelihood ratio is 1.3. So we can combine the prior odds with the likelihood ratio, 10 times 1.3, to give us the posterior odds. We can now say it's 13 times more likely that this iPhone that was left behind belongs to a female. When we're presenting DNA evidence in statistical terms, there are different sets of wordings that we can use. If we take the frequentist approach, we might say something like this. The chance of obtaining these matching profiles if the blood came from a random person unrelated to the suspect is 1 in a million. If we take the likelihood ratio approach, we could say these words. The results of the DNA analysis are 1 million times more likely if the DNA came from the suspect than if the DNA came from a random, unrelated person in the population. And using the Bayesian approach, we could take the prior odds. The prior odds is multiplied by the likelihood ratio to obtain the posterior odds in favour of the prosecution hypothesis. You can read more about this in section 2C, Subtleties and Fallacies.